Okay, let's take a look at example 4, part 2, where it says let's make A, B, C be any sets and prove or disprove the following identity. If you take a look at theorem 6.2.2, you will notice that this problem looks a lot similar like the distributive property. So I feel like this one is going to be a true statement, and I'm going to try to prove it. Okay, so the proof is going to be using the algebraic method. Okay, so let A, B, C be any sets, and I'm going to start with the left-hand side, and I'm going to try to prove that the left-hand side is equal to the right-hand side, or the right-hand side is equal to the left-hand side. Now, if I get stuck and I can't go anywhere, I'm going to stop my work and start over from the other side. So left-hand side is going to be A intersected with B minus C. So right off the bat, I can use the I can use the set difference to rewrite the minus. So I could do A intersected with B intersected with C complement. This is automatically true by rule number 12, which is called set difference. Now with that in mind, I can now kind of rearrange some of these things. I can use my associative property to go A intersect B, parentheses around that, intersect C complement. This is true by the associative property, which was rule number 2 or law number 2. And then finally, I'm going to write A intersect B and then minus the C, because if I have intersection and then I have a complement, that's the same thing as a minus by using rule number 12 again, set difference. Okay, so I'm going to pause here for a moment. I'm going to kind of keep it on the back burners, and then I'm going to go look at the right-hand side. I'm going to try to break the right-hand side down, and hopefully if I break it down enough times, it will match with this one. Okay, why am I stopping here, by the way? I've tried it already a couple times on my own, and it's very difficult to proceed forward from this step. So this is the reason why I'm stopping and starting over with the right hand side. And again, it shows you a different style of proof, and this is perfectly legit also as well. So in this case, I'm gonna begin again by rewriting the minus. Okay, so I don't like this minus right there. So I'm gonna go ahead and do A intersect B, and then turn the minus into an intersection with A intersect C complement. Now this is true by rule number 12. Okay, now let's use De Morgan law to take the C on the outside of the parentheses to the numbers inside. So this is going to be A intersect B, intersect with A complement, union C complement. This is true by De Morgan's law, which is rule number 9. Okay, so far so good. What's going on now is I'm gonna pretend like this A intersect B is 1 unit, and I'm gonna just distribute it over the second parentheses. So by doing that, I'm gonna end up with A intersect B intersected with A complement, and then the intersection sign that was on the outside is gonna end up in the inside, and the union that was on the inside is gonna end up on the outside. So again, A intersect B is going to be intersected with C complement. Okay, so again, let me point them out. The intersection that was on the outside ends up being inside the two parentheses, and the union that was inside the parentheses ends up being in the middle. So far so good. All right, now we have intersection on this first parenthesis, so we're gonna go ahead and write it down as A intersect B intersect A complement. This is true by the associative law. Union, and I'm gonna do a couple of things here. So this first of all, this previous step was true by the distributive property, which was rule number 3, and on this step I'm gonna just leave it as A intersect B and then intersect C complement. Okay, so what did I do right here? I just cleared out the parentheses from the first problem, from the first set of parentheses. This was true by the associative property, which was rule number 2. Now, why am I doing that? I'm doing that because now I have A intersected with A complement, which together, that's gonna be the empty set. Okay, how do I know that? I know that because of rule number 5, the complement law. Okay, so rule number 5 allows me to take those two and remove them and keep everything else pretty much the same for now. Okay, this is true by rule number 5. All right, well, now the intersection of the empty set with another set is gonna be the empty set also. And this is rule number, let me find it. Intersection of an empty set with a set is what we call the universal bound law, which is rule number 8. Okay, so the empty set, that's true by 8. Union, the A intersect B, still intersected with C complement. But the empty set union anything is the thing itself. So A intersect B, intersect C complement. Okay, this is true because of rule number, let me think, rule number 4, the identity law. And finally, this reminds me of what we wrote over here on the other side. So we're gonna rewrite it as A intersect B minus C. This is true by rule number 9. The set difference, if you have a minus, that's the same thing as intersection and a complement. And keep in mind that now the result of the first table that we made is identical to the result of the second table that we made. So that means that the two sides are equal. So left-hand side is equal to right-hand side, which ends up proving the problem that we wanted. So QED.